My name is Kelly Papel, Technical Manager for Invino Engineering, LLC, located in Tampa, Florida. We are a domestic and international engineering firm, specifically focused on steam and condensate systems. This is part two, the pressurized condensate recovery systems. Again, a solution to increasing the steam system thermal cycle efficiency. The example of a standard condensate system, and we'll take an application to come up with the cost benefits for implementing a pressurized return system. So we'll give an example. The system out there is running at 190 psi. So the system running at 190 psi providing steam to these process coils right here. The steam temperature is 384 degrees Fahrenheit, and we'll say the steam flow rate's 9,000 pounds per hour. Operation 724, and 7 days a week, 24 hours, and 365 days a year. As we come through the drain devices, steam traps or control valve, the condensate is going to come down into this tank, and it's going to be at 384 degrees temperature and atmospheric. There's going to be a percentage of it going to change from liquid back to flash steam. We'll say that percentage is about 18.3%. On a standard atmospheric system, that flash is just allowed to go to atmosphere, and that's a sizable loss. So if we look at the calculations, this is the vented condensate receiver allowing the flash steam to be vented. If we did the calculation, SH minus SL divided by LHL, which is latent heat low. So sensible high at 190 psi and sensible low at atmospheric 180 BTU, and then the latent heat energy low 970. When we do the calculations, and we'll come up with 18.3% flash is going to occur. So if we take that times our flow rate, we come up with 1,647 pounds of flash going to be vented to atmosphere. Well, we'll say it costs us $7.50 per 1,000 pounds, and we come up with a loss just in the flash steam of $108,000. So this here is going to be $108,207 per year. So if we look at understanding the standard condensate system losses, again, we have flash steam losses here of 108,000. Flash steam, and we give you condensate loss. For every pound of steam that we vent to atmosphere, we have to make up with a pound of water or makeup water. And the makeup water does have a cost. So we'll say 4,360 $4,336 per year at 15 cents per gallon for preparation costs of the makeup water, and that's water, chemical, etc. Then the energy to heat the makeup water back up to the deaerator operation, and we got $19,168 per year, and the deaerator we said was operating at 10 psi. Then energy to heat the condensate coming back, which was 7,353 pounds, and that's the 9,000 minus the flash steam, and we come up with a cost of $11,431 per year. So if we add this all up, then we got 108,000 right here for the flash steam losses, 4,336 for the makeup water cost, 19,168 for the energy to heat the makeup water back, and $11,431 to heat the condensate back from atmospheric conditions, which is 100 degrees C or 212 degrees Fahrenheit, and we end up with a total energy loss per year, $143,142 per year. And the other note, this is a small process application. It's only 9,000 pounds per hour. So we look at a pressurized system. And the pressurized system, we're looking at coming off of the process coils and then going through the drain devices, steam traps, or control valve. But we're operating the condensate tank here at 125 psi or 353 degrees Fahrenheit. So the condensate is coming down in here, and we're controlling the flash. Now, to consume the flash, we take the flash steam and we provide that to the deaerator because the deaerator needs steam to heat up the condensate coming back at atmospheric conditions and to make up water. So we're consuming the flash steam there. Now we can take the condensate coming off this tank and pump it directly back into the boiler. Any condensate that's not been exposed to atmosphere does not have to go through the deaerator operation. So a pressurized condensate system, we're not allowing flash steam losses. We're consuming it into the deaerator. Keeping the sensible energy in the condensate, elevated and going right back up into the boiler. And the other thing is controlling flash steam at a point the flash steam can be recovered into a deaerator or cascade system or some other method instead of venting to atmosphere. So we're controlling all those aspects of it. Now, the thing is that the pressurized system really has to be looked at as a total system. And the failure with pressurized systems, people only come in and look at certain segments of the system. Really, there's 14 different points out there that we look at. The operating pressure of the boiler, the fuel input, the steam flow to the header. Again, there's so many points out here in the system that has to be looked at, and everything has to be detailed out to make sure the system's going to work correctly. So the minimum is 14 points, and we've done as many as 35 points in the system to look at all the dynamics of the system to make sure that the system will work correctly. Then we take this information here and we input it into our software system, and we just took another example here, and the example here was an atmospheric system, and we came up with a total energy loss of $226,000 in energy loss. But the system here, the software system, analyzes everything in the system with the calculation. So when we calculate out the implementation of a pressurized system, we give a very conservative number of what's going to be achieved in the steam losses or energy reduction. And that really gives us a good number for the payback in the system. So here we have $226,701 to work with for implementing a pressurized system. So here we go into the system after implementation, so we can put into the software all the dynamics we're going to change in the system, what pressures we're going to come back and operate at, and then we come up with, zero losses now because we're recovering the flash, we're bringing the condensate back, and really the dynamics of the system is balancing out. So the point is it has to be looked at as a system, and everything has to be calculated out. So what the cost benefits are. There are no fuzzy numbers. People always come into the plant and says this is going to save you 5% or this is going to save you 3%. Everything in the steam and condensate system can be mathematically calculated out, and that's what you need to do to make sure that the project's going to pay for itself. The last is our contact information. Our approach is we're a part of your team, and we have short-term impacts and long-term impacts, and we're here to help you out. And this is our contact information. So please visit our website. We have all information is generic. And there's no vendor information on our website. So it provides you great calculations and information on implementing different things in the steam system.